Hello, everyone. Welcome to Examining Origins. I'm here with Dr. John Hartnett, who is a physicist. He's been a professor, and he's written, I think I have my numbers right, 200 papers related to physics and topics related to cosmology. He's written this book, Dismantling the Big Bang. And so I'm really excited to have him on today. We're going to talk about the problems with the Big Bang. And so welcome, Dr. Hartnett. Thanks for being here.
Yeah, thanks for having me.
Yeah, so I wanted to just start with, I was reading on your website and you used the word fiction a lot with regard to elements that are part of the Lambda CDM model, the Big Bang model. And so I was wondering could you talk about what you meant by like elements that are pure fiction?
Sure. Yeah. Okay. In fact, if you put up that second slide, cycle through. Yes, this one here. So, as part of the Big Bang model, we have to understand what is behind it, and the highlighted items on this page here are what actually Dr. Richard Liu, he's from the University of Huntsville in Alabama, he said these are all unknowns. And so these are some of the fictions that I'm talking about. Galaxy redshifts, this is the idea that if you look out into space, you look at the redshift in the light from galaxies, the further out you are, the greater the redshift. And of course, that is explained with this concept of expansion of space. But no laboratory experiment has ever measured space expanding. That's a fiction in itself. Then there's the cosmic microwave background radiation. That's real, of course. Everything on the left here are real observations. But it is explained as the afterglow of the Big Bang. Now, I contend the Big Bang didn't happen, never happened. So you can't have an afterglow of something that never happened. In fact, it's circular reasoning because they say, well, what else could it be? Well, the problem with cosmology is that you can't interact with the universe. You can't do a measurement on the universe. You're subject to what you observe. And so there are many different theories, different models that can explain the same observations. So this here is another fiction. It's unexplained in the laboratory. And then there's the rotation curves of spiral galaxies. Well, this is a strange phenomenon where the speeds of the stars in the spiral arms of pretty well all spiral galaxies, and it's also in sphericals and clusters and so on, they move too fast. And the Newtonian laws of physics, which are very robust everywhere else in the universe, it doesn't seem to apply to the spiral arms of these galaxies. And so they've proposed the existence of dark matter. And dark matter is not just like matter that you can't see because it doesn't glow. It's matter that has the property that it doesn't interact with any electromagnetic radiation at all. It only has one property, and that it gravitates. So this is a fictional concept. And the best you can say about it is it's an admission that the physics is wrong, that they don't have the physics right. So there's another fiction. And then the next thing we look at here, number 4, the distance measurements determined from these type 1a supernova, they seem to have this trend of being dimmer than they were expected to be. Now, this is back in prior to 1998, where they were had developed this idea of you selectively choose a special set of type 1a supernova, that they could act then as a standard candle or standard light bulb to measure the luminosity distance of these galaxies, that's the ones which have these supernova, well, the luminosity gives you a distance as a function of redshift. And they found that they were dimmer than they expected, and then they posit that the universe is actually accelerating in its expansion. And where does that acceleration come from? They had to invent another entity, fictional entity, called dark energy. Now, it's not just another form of energy, because number one, it's not observed, again, in any lab experiment, but it has a property that's the opposite of what you would expect any normal type of energy to have, and that it anti-gravitates. It repels the galaxies apart. So it's some sort of exotic energy that's unknown to local physics, and therefore it's fiction. And then we come on to these other problems, and there's a few of them. And one of them is called flatness. Basically, all that means is, why is the universe Euclidean in space? So that's cosmologists will call that flat, not curved. So and we don't understand why that is according to their measurements. And remember, this is also how you apply the model to the data that you're looking at. And another problem there is that the universe is uniformly, this is the galaxy distribution, is uniformly distributed in a isotropic way. It means in every direction you look, it seems to be quite smoothly distributed. And based on the idea of a Big Bang, which should have been more of a chaotic explosion of space, expansion of space, remember, that's what they believe in, then there's no reason for it to be Euclidean or isotropic. That uniform distribution just shouldn't be there. It should be chaotic and random and disordered. So this is now explained with this cosmic inflation event. Something like, what was it in Planck time, some 10 to the minus 34 of a second after the Big Bang, you had a 10 to the 26 factor cosmological expansion. And that also has many other problems. Why did it start? How did it start? How did it finish? So this is, again, just grabbing something out of the air to explain something that couldn't be explained. And this is, again, another one of those fictions. So these are all unknowns in the universe.
Okay. So, this is interesting. I want to just talk about this dark matter thing for a minute, because, when I bring this up to people that, I say, look, we haven't observed this. It's supposed to be matter, but yeah, we build these machines and everything to try to, observe this matter in some way, and we're coming up with nothing. So, I say, I think it's a made up thing. And then usually the response I get is, well, it doesn't matter. Like, something is there. Like, we don't know what it is yet, but something is there. But you're saying, no, it's actually a sign that the physics is wrong. And they're really kind of standing firm and saying, no, but we know because of the math that it's right, and there has to be something there. So what do you say to that response?
Okay, right. Now, firstly, I'll get into that in a second, but we have to understand that cosmology, and that's what we're talking about, looking at large-scale structures in the universe, it's not astrophysics. In fact, it's not even really science, because you can't do, you can't interact with it, you can't do measurements on it, and it certainly doesn't fall into the category of astrophysics. So what's happened on every scale in the universe, they've had to create the need for this entity called dark matter. And it didn't start on the large scale structure of the universe, which that other pie graph indicates. Can you want to flip that one up, that pie graph? Yep, that one. So that's the current state where they say we're at right now, that the mass energy content of the universe is 24% dark matter. And then, of course, there's that 71.5% of dark energy. But the dark matter is found on every scale in the universe. In those spiral galaxies, it's found in clusters of galaxies, superclusters, and on the very largest scale. But even more importantly, dark matter is invoked for the formation of stars, for the formation of the clusters of stars, of galaxies, and then clusters of galaxies. That it's invoked for the initial formation of structures that eventually formed into stars and galaxies, even from right the early phase of the Big Bang, because none of that would happen under the known laws of physics. It just doesn't happen. It can't happen. In fact, the known laws of physics defy any type of collapse of a molecular hydrogen gas cloud into a compact compressed object that would start to switch on nuclear fusion like a star. It just doesn't happen. So it's invoked on every scale. And it's a fiction. Now, look, there are a few scientists, I've been in the room of a lecture where occasionally one of them will say it's a placeholder for the physics we don't understand. Now, that's the more honest one. And there's been a few papers even published recently. There's a guy who's come out with a new cosmology where it's called CCC plus tired light. I can't remember something. He abandons the standard Hubble expansion constant and introduces a sort of a changing coupling constant, but he then uses tired light to explain redshift. So he actually says in that there's no need for dark matter. There are various people who say this, but they are in the minority. So what he's done is change the physics. Instead of invoking dark matter in the standard model, he's changed the physics. And this is the problem. Go ahead.
Well, now I wanted to ask, so if we didn't need it, like if we put origins aside, like if we said, okay, let's just assume that, things are just the way they are, however they got there, right? Then do we need to have dark matter just from what we're looking at right now? Like
No.
So there's nothing we're looking at right now. It's all about the origin, maintaining the origin story of the Big Bang and the possibility of getting the galaxies and the stars. That's why the dark matter is needed.
It's all about origins on every scale. And it's storytelling too, because they can't explain those origins, like origin of stars, galaxies, clusters, and the universe. You then need to tell a story. For example, you said we don't need it now. We don't, because there's no dark matter particles in the standard model of particle physics. And that's probably the most successful theory in physics. I mean, it's been extremely well developed with incredible predictions, making it's beautiful when you understand it. And we don't need dark matter particles. It's just not necessary. In fact, every time they've tried to find a dark matter particle, it's become quite absurd. During my period, I was doing experimental physics on the idea of detecting a paraphoton. A paraphoton is not exactly dark matter, but it's one of these closely related to it, like the axion, looking for the axion. And we did resonant cavity experiments trying to look for this paraphoton. Of course, these are all null experiments, and because they don't exist. So all you're doing is excluding, in a sort of an parameter space, excluding all possibilities. It's really important to understand this. There are many other contradictions that only show up in cosmology. They don't show up in the lab. For example, when you compare the mass of the universe as determined from the cosmic microwave background radiation measurements and compare that with the type 1a supernova measurements, you get completely different numbers. And they're not even overlapping on the error bars. And so the resolution to that, and this I don't want to go into much detail on that, but the resolution is that you have to invent another dark matter particle. In this case, the sterile neutrino. It doesn't exist in the lab, but that has to be invented. They call that one dark radiation.
I'm glad you brought that up, because that's what I kind of wanted to ask about next, because you mentioned the standard candle. You said the wording you used was they chose these type 1 supernovas. And so do you disagree with that choice as a way of measuring, or do you disagree with the data?
Okay.
What part do you disagree with that would say, because, dark energy, it seems crazy, all of a sudden there's something that just suddenly makes the universe, the expansion start accelerating.
Yeah.
But what do you make of the observations that led to that idea?
Okay. Look, I don't want to infer anyone in the science, in astrophysics or cosmology, is deceptive, right? But I do believe they are heavily motivated by their worldview. That's their biases. And when you look into the methods by which those standard candles are chosen, this is the type 1a supernova, they select in a sort of it's circular reasoning. They select those supernova that have an absolute brightness that fall into a very narrow band. And they have supernova are measured with a light curve. That the explosion, it explodes, it gets bright, and over time it decays away. And so you fit a luminosity versus time curve to that. And so then when you choose your candidate supernova, you look at those light curves, and the argument is that the standard candle all have the same absolute intrinsic brightness. But of course, you don't know what that is because you're not measuring next to that explosion. You're millions or billions of light years away, and so there's no way to determine what the absolute intrinsic brightness is. So you have to make some assumptions, and that's what they do. It's circular reasoning, because it has to fall within a certain band to select it. So, because you want to select all the same type, and so you have to apply your cosmology to that to determine what the absolute brightness is. And then once you've selected your group of them, you use them to test your cosmology. There's the circularity. But there's much more to it than that. Even the cohort that's chosen, their light curves don't lie on top of each other. They don't match. And so they say, okay, well, there's a sort of a natural spectrum, a natural variation. So we have to allow for that. And so they apply this thing called a stretch factor. So it's a literal fudge factor to adjust them to choose that group. But there's even another problem. in Big Bang cosmology, if you look back in space, redshifts are larger, so that means time dilation occurs. So the very high redshifts, one should have significant time dilation affecting them. That time dilation would affect those light curves. It would stretch them. So how do you deconvolute the stretching of the light curve from a time dilation effect? So you see this, it's impossible. It's actually goes to the problem of cosmology at the very highest level, and it's called undetermination. It's underdetermined. You don't have enough parameters to really solve the equation, put it that way. It's like having 3 equations and four unknowns, not 3 unknowns, 4 unknowns. You can't solve for all of them because you don't have enough information. And cosmology is like that everywhere. So that's part of the problem. So they're fudging those light curves. They have to. And every now and again, you'll find someone who will write about this and point this problem out. But, you know, they awarded the Nobel Prize in 2011 to a team of people, in fact, 2 teams, and for this discovery. And yet it's got all this fudging involved in it. You eat fudge in America, don't you?
Yes, we love our fudge. Well, yeah, and I was actually reading the lecture, the Nobel Prize lecture that Adam Rees gave about that discovery. And so he said, like, that it was when he did all the calculations with the supernova and everything, it came out as a negative, you know, in the universe, and he knew that couldn't be right. And so it was his calculations being like absurd that made him like come up with the idea of dark energy. So
yeah, so he basically had to put in the cosmological constant, essentially that, right? When Einstein had it there before, took it out, now they throw it back in. Yeah, it's essentially a constant of integration. I mean, it's valid, mathematically valid to do. But, you know, there are many theories, many other cosmologies that fit the same data. And, you know, some do or don't have dark energy and dark matter. I had to have dark matter in there too, by the way. That's essential to have that as well. Otherwise, the metric, the chosen metric, won't fit those light curves when you look at them, the luminosity versus redshift. That won't fit the equation.
oh wow. Okay. And then like the other fictions that you mentioned, inflation. So
Yeah.
you know, and that one is interesting to me because although we say that, you know, nothing can travel faster than the speed of light, in inflation, don't we have to have things traveling faster than the speed of light?
Yes, yes and no, but in this case, they're okay on that, and the reason is that concept of not traveling faster than the speed of light from special relativity is light traveling through space. Now, where I don't agree with them, what they're doing is expanding space over a very short time period. So the linear expansion was 10 to the 26th power. So that means a volume expansion of, what's that, 78, 10 to the 78 volume expansion in 10 to the minus 34 of a second. I mean, these numbers are just totally mind-boggling. But in that case, though, in that space, the speed of light, it would still, within the space, the speed of light should still be the limiting factor. But there have been problems with that too. And so there have been alternatives suggested of superluminal light speed, even in the early Big Bang universe, to try and accommodate that. Yeah, but there's many more problems with cosmic inflation. I don't know if you had it on your list, but the horizon problem. You're aware of the horizon problem. I mean, the horizon problem is solved by cosmic inflation. It's basically the problem of, in a Big Bang universe, that in every direction, it seems, on the largest scales anyway, the universe is isotropic. I mentioned that earlier. And also the cosmic microwave background radiation coming from opposite sides of the universe is very uniform in temperature. It's not higher from one direction than the other direction. So that implies whatever the source of that radiation is, or let's say the radiation itself, has mixed up in the universe to equilibrate it, equalize it, all down to that same temperature of around 3 degrees Kelvin in the solar system locally. How did that happen if the universe has not had time for that to occur? And so that's the argument. So if you're looking out at the horizon in any direction, you're seeing light in all parts of the spectrum, including the cosmic microwave background. You're seeing that for the first time. And so it hasn't had time to mix up. And that's why it's called the horizon problem. So to solve that, you do that supermassive expansion over a very short time.
And is there any evidence that inflation actually happened? Or is this just another thing that we need in order to keep the model afloat?
Absolutely, it is something they need. Again, this is part of the problem of cosmology, that because you can't interact with the universe, I call it stamp collecting. So what you do is you collect all your different samples of, you might be looking at galaxies. You collect all the different types of galaxies and you collect them at different redshifts, and then you posit a theory that will fit that, as if those galaxies evolved over time through those redshifts. Well, it's the same problem on every scale. We can't interact, you can't send a signal, so you're only limited by the information that you have. So you can have observational evidence, though, to test your model, but you shouldn't then invent unknowns when your model doesn't fit. And that's exactly what's happened. They've invented all types of unknowns, and I say that cosmic inflation is one of them. Now, I mention it that way because you might recall some years ago there was this telescope, well, it's still there, at the South Pole, the BICEP 2 telescope, where they were looking at the polarization of cosmic microwave background. It's the spatial polarization across the sky. And they claimed there was evidence in that for the leftover from that inflation period. At the time, I predicted that that would be retracted. And I think within 3 weeks, it was retracted because it was clearly a local effect, some local disturbance in the signal. It's, in my opinion, it's beyond credibility to say that anything you observe here, remember our telescopes are all on Earth or in Earth orbit in the solar system. And it's incredible to me to make a claim that you're detecting something from the, and I say putative, Big Bang, because it never existed. And so that's the limitation of cosmology. It's, as Richard Liu says, it's not even astrophysics. I go further, it's not even science.
Wow. Well, there's so much talk, if you just Google the Big Bang, you'll find so many videos, so many articles, and people talk with such assurance that we have so much evidence for the Big Bang. In fact, I saw Roger Penrose and some other scientists on a stage, and they were like, "If you don't believe in the Big Bang, we don't let you on this stage, ha 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 ha, because you're just stupid." Basically, they were just laughing off this idea that anything could be against the Big Bang. So, what do you make of all this? Talk, like confident talk about the model when it seems to be so riddled with problems.
Yeah, absolutely. It is riddled with problems. Look, so let's talk about their two best evidences, right? Number one, George Gamow in 1948, he predicted that there should be an afterglow, an echo of the Big Bang. And he said we would find it at a temperature, this is a thermal radiation temperature, of about 5 Kelvin to 50 Kelvin. He made various predictions over time. And before 1965, with Benzias and Wilson's discovery of the cosmic microwave background, he had reviewed up his number, temperature, on the high end, 50 Kelvin. So it's sort of a half right prediction, because by that time he was sure it would be much hotter than what they discovered. In fact, the discovery was serendipitous. They weren't looking for it. In fact, they didn't even understand it. I think it was might have been Peebles from Princeton that had to explain it to them. I'm not sure. I might be wrong on that, but they didn't understand it. Okay, but let's put it down as half right. And then the other one is this idea of the redshift observed in galaxies, that we see there is a overall trend, a general overall trend of as the apparent luminosity decreases, sort of indicating farther away in the universe, that they have a higher and higher redshift. So then that is claimed as a Hubble law relationship, distance and redshift. It's really a luminosity distance and redshift. So you have to then apply your theory to generate a distance. And to apply your theory means to apply your cosmology, which means to accept a certain portion of dark matter and dark energy. Otherwise, again, a bit of circular reasoning in that. Okay, so that's their best line of evidence. But Hubble himself doubted that the redshift implied distance. And he wrote about this several times over the years after those early discoveries. In fact, he even suggested it might have been something intrinsic to the source. Well, I have a friend who, over the years, he's a Big Bang skeptic. Actually, he's not a believer. He's not a believer in the Lord, in a creator, but he's a skeptic on the Big Bang. And I think the last time I saw one of his writings, he had got up to about 40 different possible mechanisms for redshift. And not all of them would apply it to a galaxy, but a lot of them would. And because we know in the lab, we've established in the lab many different types of, we could say, redshift mechanisms. We have gravitational redshift, which is well established with using ultra-stable clocks. We have a whole host of different redshift factors that come from other techniques in physics. Yet, this expansion of space idea of redshift, that has not been measured in a lab experiment. So the one mechanism that's almost universally relied upon for the basis of the Big Bang is that over time the universe gets larger, therefore redshift implies distance, and that has not been measured in a laboratory experiment. Well, there's contradictions even in cosmology. When you get to quasars, for example, quasars have very large redshifts, and yet there's evidence, physical evidence on this, looking on the sky, of associations of quasars with galaxies, like quasars embedded in the arm of a spiral galaxy, or even quasars that seem to have proper motion. To an astrophysical object to have proper motion, it must be close. It can't be enormously distant, like on the edge of the visible universe. There's so many strange phenomena that contradict that neat little Hubble law concept, you know.
Okay, so you're saying the two pieces of evidence that they use, the cosmic microwave background, which could be radiation coming from something completely different. It might not even be the Big Bang, and the prediction wasn't very good.
Yeah.
And then the redshift is interpreted as expansion.
Yeah.
And we actually don't know what the redshift is. It's real. The redshift is a real phenomenon, but we don't know what actually causes it.
Correct, because we can't measure it in a lab experiment, and there are many potential mechanisms that could explain it. Yeah. But back on the
cosmic microwave background, and
yeah, there are contradictions there too. And you may have heard of the axis of evil. By looking at the data, starting really with the WMAP satellite, and then later with Planck, you can map the sky with the anisotropies. They're the fluctuations in the radiation or the thermal temperature fluctuations. You can map that on the sky, and then you can do a spherical harmonic deconvolution. It's like fitting a multipole expansion terms. So it will have a dipole term and a quadrupole, octopole, and higher order expansion terms. This is just spherical harmonics in mathematics. When you look at these terms that you can generate from that, there's some strange stuff that developed, starting with WMAP. And they found that I think all but one of the octopole has 4 axes, quadrupole has 2, and all but one of those axes were aligned with each other and aligned with the ecliptic, with the plane of the orbit of the planets in the solar system. And that was dubbed the axis of evil, not by me, but by the astrophysicists themselves. Because that's like saying that the solar system somehow has influence on this cosmic microwave background radiation that is everywhere in the universe, but the solar system is not. It's like putting the solar system into some unique role, special unique role, which defies description.
So it would be very unlikely that it would happen to line up with the solar system if it's really coming all the way from the edge of the universe.
Yes,
that's the point.
That's correct, but it's a little bit more than that. It's a little bit more subtle to understand that if in a Big Bang universe, the cosmic microwave background radiation is from everywhere. The center of the universe in a Big Bang universe is everywhere. There is no center. There's 2 ways of saying it. There is no center, or the center is everywhere. So the ubiquitous radiation, the assumption is that it's in every part of the universe, and somehow the plane of our solar system, and it's more than just the plane of our solar system, it actually aligns with the equinoxes, because the Earth's orbit around the sun is the tilt of the Earth's axis is not in the plane of the solar system. It's tilted out of it. And so twice a year, it actually aligns with where the equinoxes crosses the ecliptic, crosses that plane. That is bizarre, really bizarre.
Wow. Now, what is the like if we don't accept that cosmic microwave background, if we're trying to come up with a different interpretation of that, what is this coming from?
Look, I'm, I can speculate. And I have done for some time. I've developed some of my own ideas. But if we look in the biblical account of creation, on day one, God created the earth first. Interestingly, it's called earth. Actually, it's a ball of water. It's just water. And in space, that water would form a sphere as soon as God creates the laws of physics, which I believe he did right from the beginning. Then it forms into a ball of water that will cool rapidly in space. It will come down to equilibration. The thermal radiation will travel out from that sphere, and the sphere will be a solid ball of ice. And it could be that that is the source, that it's cooled down to 3 Kelvin, which is the CMB radiation is basically telling us that's the ambient temperature of space, that away from stars, in the darkness, away from all that stellar radiation, matter, black body matter, glows with a thermal temperature of 3 Kelvin. Well, that initial creation of the ball of water earth, ice earth, would radiate at that thermal temperature of 3 Kelvin. So what if, now I said I speculate, what if that is the source? So we are seeing in the CMB radiation, we are seeing a signature of the initial creation. And that radiation can only travel out to several thousand light years from Earth, because it's at the Earth that God started the creation. That's the whole creation is around the Earth. And so that radiation would travel out. It would become, it's like a cavity in space where that radiation exists. Well, we haven't measured outside even the solar system, so we don't know. You can't say it's everywhere when you haven't made the measurement. So maybe it's a signature of the initial creation.
Okay, interesting. Well, I want to put this other slide that you have up because I think this is in response to, I asked, can you talk about the evidence for the universe expanding? Is that what this slide is related to? Okay.
Correct.
So you've made kind of a pro and con list here. Do you want to explain?
Yes. Okay. Mm-hmm. Okay. So the first one is the Hubble law, right? So now we're talking about with respect to whether or not this concept of expansion of space is valid. Well, I put that as a pro for that because it's derived from general relativity. So that's a tick. So we can get that from general relativity. And then the second one is the type 1a supernova. On the face of it, that data does fit the Hubble expansion when we apply the cosmology, the standard lambda CDM cosmology, because that's implicitly, though, making assumptions that dark energy and dark matter are real, that they exist. So that gets a pro in that case. But
can
dark energy.
There for 1 minute?
Go ahead.
Just to clarify. So are you saying that if we just took our regular observations of the supernova and we don't factor in dark matter and all this stuff, then it's not a pro for expansion?
It won't fit.
Okay.
What would happen is when you try to fit your theory to data, to observational data, you'll need, say, too much matter. You'll have to have way more baryonic matter. And that's indicative of the fact that they had to invoke dark matter. Dark matter is what, 21%, and baryonic matter is like 5%. So it's like 4 or 5 times the amount of matter. It's insufficient. So that means it would fail. The theory would fail.
So what happens if we just took the observations of the supernova and we just used the observations without adding in any of the other entities?
If we did that, then we would have to put a cross there on con.
Okay.
It would be a failure. But I mean, I base this on what they are doing, So I'm giving in the second line, I'm giving them the benefit of the doubt, but then I'm looking at the dark energy and dark matter in the next two, which go against that.
Okay.
Because they're unknowns. So that sort of works against the idea that that's correct. And the next line is a particular supernova event that was looked at in great detail, and they found that there was no time dilation. So this problem with supernova is this stretch factor and time dilation, and it's impossible to deconvolute them. But they did find one supernova where the time dilation was in favor of no time dilation, which they need. They can't have it. And even that is very strange. But, okay, you've got one data point. The next one is called supernova metallicity versus redshift. Metallicity, metals in astronomy are anything, any element greater than lithium. So essentially hydrogen and helium, a little bit of lithium, but hydrogen and helium are not the non-metals, and everything else is a metal. I know it sounds strange. But so you can have models that predict that as you look back in space, stars and galaxies should be more made up of just hydrogen and helium. They should be like young stars, young galaxies that haven't evolved, that the stars haven't built through fusion processes and supernova. They haven't built up the higher elements in the periodic table. Well, those measurements contradict the expectation, that scheme. Metallicity is high in high redshift supernova, quasars, supernova, high redshift supernova. I already mentioned quasars exhibit proper motion. Some of them do. So they shouldn't. They should be, because they're very high redshift, and so they should be the most distant. Quasars have luminosity variations, some of them even very short timescales that defy explanation if they're the size of a galaxy. The fluctuations in their luminosity is too fast, and so that seems to indicate that they're not as big, and if they're not as big, their luminosity is wrong, and so if the luminosity is wrong, then the luminosity distance relationship is also wrong, and that leads to the problem of spatial expansion. The next one is gamma ray burst luminosity variations. Again, these objects also have large luminosity fluctuations that some of them in line with the size of a galaxy, others not. And that's why that's equivocal on that point. Though they are used, GRBs, are used to fit to the standard cosmology as a very, very bright explosion in space. The problem with those is there's no way to calibrate them to an absolute brightness standard. And so there's often a little bit, again, circular argument. You go looking for a solution to a group of them, and then you calibrate them from your cosmology, and then you use them to test your cosmology. Circular reasoning again, unfortunately. Angular size versus redshift. Now, this is another problem because angular size also depends on cosmology. You can measure a certain size, but then you test it against the cosmology of what you expect as a function of redshift. Now, there have been people who have tried to use this as a test against expanding universe, a test for a static universe. And some of those measurements have been quite promising, but they're also faced with the same problem. Because you see, angular size is related to surface brightness, and surface brightness then gives you luminosity. But to choose a group of galaxies that have all the same absolute luminosity, in this case, this is what it is. It's with galaxies, not with supernova, but with galaxies. To choose them, you have to somehow know what their intrinsic brightness is. So they are selected, they start with large data sets and throw away everything that they think is not conforming to a certain type. So you look at spectra, you look at all different morphology and everything, try and choose a set that you believe has the same intrinsic brightness. But you can't absolutely know what that intrinsic brightness is. However, those measurements have been able to show that you could have, they're consistent with a static universe, put it that way. And yeah. The next one is...
They actually, do they contradict the Big Bang model? Because you have them under con. So
yes, of course they do. Everything under con is contradicting it. They're all in favor of a static universe, of, let's say, they're not in favor of an expanding universe. That's right. Mm-hmm. And so, yeah, so what the Big Bang model would do with this variation in angular size or surface brightness, they would explain it with the evolution of the galaxy. This is the knob in the theory that you can turn, and you say as a function of redshift, oh, that galaxies or that class of galaxies that you've selected, they have evolution as well. That means they grow in size and complexity, and therefore they grow in surface brightness, because they're more massive. The more massive they are, the brighter they are. And so this is the problem. It's again trying to solve those four variables from three equations, three unknowns, and four unknowns, but trying to find, yeah, you know what I mean? You don't have enough.
That actually kind of brings me to asking you about the recent observations with the JWST. I don't know, do you want to finish this chart, or is it okay to ask you that right now?
Yeah, that's fine. I mean, there's a lot more detail in there than I thought we were going to go into anyway. But yeah, look, the JWST observations, I'm talking about the ones with high redshift galaxies. These defy standard Big Bang interpretation, because they seem to be uniformly saying, maybe bad choice of words there, that the most distant galaxies that they observe are too big, too smooth, too circular or spherical. They're what they would call mature galaxies. Now, I don't subscribe to this concept of young and old galaxies. That's intrinsic to the idea of evolution of galaxies. But that's how they're described, even in the secular press, because you get to within, I'm not sure the numbers, 400 million years of the Big Bang, and they're saying we see fully formed, fully mature galaxies at that stage of the history of the universe, which just should not be so. According to standard theory, what should happen is you start with a chaotic mess of gravitating bodies of stars. It's chaotic, it's lumpy, it's disjointed, and as they grow, they form into more smoother, spherical or circular, orderly structures and grow over time. They start small, and as they grow larger and larger, so therefore they would be at lower and lower redshifts, meaning closer and closer to us, where time has passed from the Big Bang. So high redshift means far long time in the past, lower redshift means more recent, and we should see bigger, more complex, yet heavier, more massive and more luminous. But the trouble is, what we see in the James Webb observations at the very high redshifts is more of a mixture of what we would call mature and maybe less mature galaxies, the type that we see around us in our galactic neighborhood. So it's a sort of the similar kind of a mix. And you'll find people reporting this where they'll always add the caveat, yes, but we know the Big Bang is still true. The Big Bang is the best explanation, but we can't explain this. Well, there are a few theorists again. I remember Michio Kaku, the theorist, was talking last year about this, where he was basically saying this is one of the biggest discoveries in cosmology, and it's time to rework the theory. And he's a theorist. So, you know, they understand the ramifications of this. The Big Bang is a failed theory. They have to keep propping it up. And it's like any theories that have gone on through history in physics, the more and more problems develop against the theory, the more epicycles they have to add. That's what they had to add with the geocentric theories from Ptolemy and so on. They had to keep adding the epicycles, these sort of caveats, you know, special conditions. And that's the problem. Dark matter and dark energy and cosmic inflation, they are these epicycles. So I'm looking forward to more James Webb observations, because I think the more and more we get, the better the biblical creation model is going to be. And if I can just take a second to explain why that is. Look, biblical creationists also have different theories, different models. We don't all agree with each other, but the Bible tells us the universe is less than 10,000 years old, just based on the genealogies in the Bible. Now, we don't have to argue over exactly how many years, but that's nothing compared to 13.8 billion years or 14 billion years since the alleged Big Bang. Well, in a biblical creationist model, there's no reason to posit that galaxies evolve at all. God just simply made them the way they are. And there's good biblical evidence for that God created and we see it. So this goes into another issue. So maybe for another time we could talk about the light travel time problem. But my model is simply what we see in the universe, we see it in real time, and we would expect a mixture of all different types of galaxies. That would be a prediction of a creationist model. Certainly the one that I now believe is correct.
Wow, thank you so much. That's wonderful. This has been really great, and I actually have more questions if you want to stick around a little bit longer, or do you
Sure.
prefer to save it for a different show?
No, that's fine. Ask
Okay.
away.
Okay, well, you mentioned, the galaxies not being what they expected when they looked out with the JWST. So, and anybody who's watching this, you can go right now and look, just Google, the model of the universe, and you'll still see this little conical thing that, they've put in, and you'll see it, a couple 100 million years after the Big Bang, supposedly. So there shouldn't be any galaxies there, but we're finding galaxies that are at that point in that time period. So
Can I just, Rebecca,
yeah,
just add, that's if you assume the Big
right,
Bang cosmology is true, that's where it would put it in that time period. So that's their model, right?
right, in the model, which
Yeah,
we are not agreeing with that model. We're saying
exactly.
no, this is not, we're not looking out and seeing the beginning of the near the big time of the Big Bang, because there was no Big Bang. God created the universe, and so these things were formed. So, but if we're going by their model, there shouldn't be those mature galaxies there. There shouldn't actually be any galaxies there, but much less galaxies that were supposed to take, according to their model, 7 to 9 billion years to form. So it's problematic, and they already started having problems with that when the Hubble. But what I've noticed is they're admitting that, okay, we need to rework our galaxy models. I've noticed that they're admitting that, we didn't expect those galaxies there. We see the galaxies there. Okay. But what I don't hear anyone admitting is what I hear Eric Lerner saying. Are you familiar with, like, what Eric? Okay.
I know him.
Oh, good, good, good. Great. So, you know, on I've been listening to what he says about it, and he says, that when they do the Tolman surface brightness test, like you mentioned on your list,
Yeah.
that actually if you calculate in the expansion, then when you put that calculations in, those galaxies that they're observing would have to be impossibly small, impossibly massive, that the it does not make sense with our observations. And so, like, it's a problem with, the how the turnaround point should, we have to add in a calculation for the expansion model. So I don't hear anyone admitting that. Can you
Yeah.
explain what's going on with that?
Well, it depends. Again, it's model dependent, right? Your cosmology and standard model basically get past a certain point, and the angular size of the galaxy should actually get larger. Whereas they're observing, well, it depends. Sorry. Yeah. It
It,
depends on the cosmology. This is the problem. So I really don't want to say something that may not be true. But he's quite right. They have to apply their cosmology to that particular situation, and that's all part of that circular reasoning concept again. Yeah. So look, I don't want to go into detail because I would have to review that to be clear on that. Yeah.
okay, but do you hear anybody admitting that problem, like in your circles and
No,
stuff? No.
no, no.
Okay.
All I hear is some people saying we need to rework the theory, that sort of thing. But what he has pointed out over many years is this issue to do with surface brightness, and that is a problem, I believe. In fact, his arguments, I can say, going back many years, Well, one of the arguments that adding to everything else I knew led me to believe that the universe is in fact static. I used to be right into an expanding universe model, not standard Big Bang model, but different alternative models. But I'm quite convinced now that Eric Luna is correct, and that the universe is actually static.
And you mentioned, is that because I heard you mention the Euclidean, like we see the our observations of the universe are that it's Euclidean, but then I always hear people talking about relativity, and that means space has to be curved or something. I might be getting that totally wrong. Do you mind explaining what our observations are showing about that?
Okay, so when we talk about Euclidean space, we mean the spatial component of space-time. The spatial component is exactly Euclidean. And that's a big problem. I don't have the numbers on me, but according to the standard model, the universe has to remain within that flatness or Euclidean. So that's where the density, the total matter density, excluding dark energy, the matter density is equal to 1. 1 here is what's known as the critical density. And it has to remain within something like, I'm guessing here now, something like 10 orders of magnitude within that critical density. So in other words, it's 1 plus or minus 10 to the minus 10, some critical density like that over the whole history of the universe. Because every observation we make is consistent with that Euclidean space. We don't see anything inconsistent with that. And the models also require that total the total mass energy density of the universe to keep it Euclidean. Yeah.
So that's part of why they need to put in the other like entities like dark matter, is to keep it at that, or?
Well, it's actually was to fit those other equations, but yeah, it is essentially the same thing, that it must remain within that critical density. Yeah, it is. Yeah.
Okay, I probably still don't understand the concept of the Euclidean space and everything. So
well, look,
we can move on from that, because I don't know if I'll understand it in
only when you get close to a compact object like a black hole or something does the spatial curvature change away from Euclidean space. But in the universe, it's smooth and flat is the idea. It's very close to Euclidean. And you have to explain that. If you came out of a Big Bang, why would that be so? Surely it could be anything. We can't explain it, And look, this is a little bit of a segue here, but the absolute fact is that if the universe is three-dimensional, then that explains everything we observe in the universe. And it also explains the propagation of light in the universe, gravitation, everything, that like luminosity changes as the inverse square, right? Electromagnetism, gravitation, these all fit inverse square laws. Well, that tells you that you have 3 spatial dimensions, and those 3 spatial dimensions are Euclidean. This, to me, I've written this into my new book I'm writing. This really is design. This is design in the universe, that God has created a universe that shows us everything is based on these three spatial dimensions. And the planet itself is spherical. Every object in the universe is spherical, every one above 100 kilometers in diameter. And everything we measure about them, that three-dimensionality, put it that way, 3 dimensions, where we can measure it, we measure it with incredible precision to be 3-dimensional. The question is, well, why? Why is it so? If it's a process of an explosion of space and time, why is that the case? Why is it such an orderly arrangement? Remember, the Big Bang universe is not created. There is no creator. And so there's no reason to assume that the laws of physics should be as they are. And so people like, what's his name, Lawrence Krauss, has suggested a multiverse. And we just happen to be in the one that has these particular laws, the particular structure of the universe, of space-time, and the particular set of laws of physics that finally, they call it the anthropic principle is what they call it, that the universe is finely tuned to life. For us, really, human life on this planet. I know that's a big segue there, but it's all connected, and that's the amazing thing. And by the way, it shows us that this planet is spherical. It's a globe.
For those who may be watching who aren't sure about that, which I don't know. I don't know if any flat earthers watch my channel, but yeah.
No.
Well, thank you so much. This has been amazing. And I really hope we can have another chat, because this is,
Sure.
I mean, I feel like on each one of these topics, you probably have a lot more to say. And for those watching, I've put Dr. Hartnett's link to his website. If you want to read more from him, if you want to learn more, you can find him at his website. And yeah, there's lots of videos on him available. From him available on the internet as well. So you can look him up. Mm-hmm.
Yeah, look, there's I don't know how many on Cosmology, but there's a lot on my website on Cosmology. Just go there and just put in the words in the search box to find them. That's the quickest way to do it, and you'll find literally hundreds and hundreds of them there, which we cover, like a lot of stuff we covered here, but in a lot more detail. Yeah.
Thank you so much. And what's the name of the book you're writing, or is it so far untitled?
No, well, look, I'll call it a working title. It's called The Physics of Creation. It's a little different to what I've done in the past. It may not remain with that title, but it is that at the moment. And I've tried to look at the whole creation from the beginning, from day one, from a physicist's perspective. Now, I know once we get into creation of life and various things, there's a little bit more, but there's a lot of physics even running through all of that. Even the curse, even the physics of the curse, I found to be very encouraging, that God he has an answer, a restoration from that. And we can see that in his creation. So I tie that into, all this talk on climate catastrophe and the design that God created to supply mankind with an abundant fuel sources, coal and oil and nuclear. All these things were supplied by God as part of his creation, and sort of bring that through to show people that the final restoration in the new earth is it's in a sense the repairing of what happened, but it's all part of his design, So there's physicists for a long time have looked for a fifth force, And there was a time where the Casimir effect, they thought that might show us a fifth force, but it's not turned out to be the case. Well, I believe that the Creator kind of has a fifth force. I wouldn't call it a fifth force, but I'll call it his sustaining power. And I illustrate that with the burning bush. When Moses appeared before God with the burning bush, the bush never burnt away. In fact, as long as the Creator wanted it to, it would have remained there burning. But the laws of physics that we know, I don't believe were changed in that. So the laws of physics I'm talking about are the laws of thermodynamics, conservation of energy, and second law, the law of decay, you can call that. That was still all operating. It's just that God was using this fifth force, his sustaining power, to regenerate what was decaying, or let's say being randomized by the burning. So the internal states were being randomized, and God was restoring that. And that's why the bush never burnt away. That's
oh, wow. That's interesting. That's
go ahead.
No, go ahead.
So that's a sort of a little microcosm of what the Lord will do in the new earth. He will restore that back to the former precursed state through his sustaining power. And I argue that that applies to the whole universe, that it's an eternal universe under that restoring power, of that sustaining power of the Creator. So you see there's a perfect balance in all this, that God created the universe in a perfect state. It was marred by sin, and then the curse was the result of man's sin. Yet God stored sufficient material and design in the creation to see us through to the time of the new heaven and new earth, when he will restore all things. There'll be no more death. Everything will be brought back to the precursed state, and the universe will be eternal. So it's completely in opposition to everything that the standard cosmologies talk about. And even we're not talking about just Big Bang here, we're talking about all the alternatives as well. Even a lot of people who still believe in steady state theory, a lot of them have no faith in a creator God. That they see the universe as the product of materialism and matter and energy and nothing more. But I see that the universe is the product of divine creation, and God is trying to show this to us in everything that he does. Yeah.
Yeah, well, I love that idea, the way that you said it about the restoration at the end, because is this what you're saying, that it's not that the laws of physics that we understand now are going to stop, it's that the additional thing of God's sustaining power is what's going to keep it from making things chaotic. Like God, the chaos. You're saying the chaos, the randomness, the
winding down. Yeah. The decay.
Wonderful. I like that.
Everything will be restored. There will be no decay anymore. It'll be that perfect paradise again. Yeah.
Now, what do you say to people who say, well, that's just a story you believe. That's just in the book. Who believes that stuff anymore? What causes you to believe that stuff?
I put my trust in the living God, in Jesus Christ. I don't put my trust in science or man's observations or man's interpretation of those observations. Yeah, I put the word of God first and his Holy Spirit speaking to me through that. I come at it from a completely different direction to any secular scientist would, but I'm not deluded about worldview issues. It doesn't matter who you are. You can be a believer in the history of the Bible like myself, or you could not be. You could be any of those variations. You could be a Christian that believe in evolution, whatever. You could be anything. It's a worldview issue. It's not. It's not evidence. It's not. The facts are all the same. It's how you interpret the evidence, and it's your worldview that is a filter that you use to interpret that evidence, right? Anyway, as you mentioned earlier, I mean, we're talking about origins here, and the danger of saying that the origin was this or that based on the evidence, that's a big danger, because it all depends on how you filter that evidence. It's a forensic science. It's not operational science, and it's what you apply, what you don't apply, and how you apply it. And there is nobody without bias. They all have their biases. Believe me, I worked in a university for a long time. I see those biases, and they're very biased. If I tell people, well, as it happened in the past, I told people I believed in the biblical creation. Now, it was okay that I was a Christian. It was okay that I believed in God, but it wasn't okay that I believed in the biblical account as real history. And on several occasions, there were the other professors. One guy was an astrophysicist, and he tried to get the university to sack me, to kick me out. But my research was first class. I was publishing enormous amount, and the executive wouldn't even listen to it. Why would that be the case? It's only because of worldview issues, because he didn't like what I believed, and this is the problem. So put the Lord first and his word. Put your trust in his word, that he knows how to preserve it, and he has preserved it. I'm not saying that everything is perfect, but I'm saying that we have a far better description of the history of the universe from the biblical Genesis account than you will ever get from Big Bang or any other unbiblical worldview. Now, I say it that way because there are many Christian organizations that promote non-biblical worldviews, even evolution and Big Bang. They're wrong, because they also don't understand the worldview issue. It's not facts, it's how you interpret those facts.
Yes, I agree. And we're not saying anybody has to accept, this view. But as the more that I find out, I realize that, this idea of young Earth, young universe, it is not as crazy as people would like you to believe that it is, right? And I mean, you're a great example, Dr. Hartnett. It's clear that you're an expert in your field. And so, you're processing, like you said, the same information, but you have a different starting point. And a lot of people are starting with naturalism. They must find a natural process by which everything came about. And so that is going to be problematic.
Yeah. Right? And link to that, people who don't have the credentials or the education or training to look into a lot of that information that's been presented on the History Channel or the Science Channel or these different channels, they implicitly accept what the expert is telling them, sort of like the expert is becoming the high priest of the secular religion. I mean, science is a religion. It's become a religion. It's idolatry, really, because they accept it without question. And so you will have even many, many Christians who just go along with accepting that the Big Bang was what the Bible was describing in the beginning, the creation of the universe. And what I'm saying is, look, I've looked into that. I was once a Big Bang believer. I was a steady state believer in high school and then Big Bang. But when I looked at the evidence and I looked at the biblical account, I came to the conclusion there's no reason why I need to throw the Bible out, but the history of the Bible I'm talking about. It does not contradict anything in the science. When you fully understand the assumptions and the axioms, the worldview issues, then you realize that there is no contradiction at all. So I say to people, okay, look into it, do more research, look to reputable, well-trained people in the biblical creation movement, and satisfy yourself. But number one, trust in the Word of God that it's true above all else, because even models, creation models, come and go. We don't all agree with each other on everything. There's some creationists who believe that dark matter is a real thing. I don't. But that doesn't mean, this is all models, and we just need to not hold them too strongly. But what we hold strongly is that God did create the universe in 6 days, and we know it was less than 10,000 years ago, and God is superintending the universe, and it makes a lot of sense that he's doing that, because he will renovate this planet, creating a new earth and a new heaven, and where there's only righteousness, the curse is reversed. There's no death or sin. Yeah, I know it sounds too good to be true, but it's what Jesus Christ did for us. He gave us that pledge, that promise, that guarantee that is the life that we will have. And he showed us that in his resurrection, that he had a resurrection body, and it was supernatural, celestial, but it had flesh and bone, as they said. It even showed the marks in his hands. So it's real. It's not like a theophany or some sort of vapor or something. It's a real body. So we will all have that. All of trust in him will have that in the new heaven and new earth. Wow, what a wonderful thing to look forward to.
Yes, absolutely. And for anybody watching who's saying, oh, see, this is just a religious channel. No, we are really looking at the science on origins. And if you're a scientist and you have a different origin view, I'd be happy to interview you on this channel and hear your perspective and talk about it and just look at the science. And so this is, an open forum for examining. We're just looking for what is true. And so thank you so much, Dr. Hartnett. This has been amazing, and I really appreciate you.
Thank you very much, Rebecca. That's great.
Yeah, and thanks those for watching, and take care.
Bye now.